G'day everyone, Richard Walding here. In this video today I'm going to have a look at the prac in electromagnetism. It's a modification of the one you might have already done. Now I've called it strength of a magnetic field. I'll just put it up on the screen. Strength of a magnetic field versus number of turns per meter in a solenoid. Now the reason I'm doing this is that some teachers have said it's been hard for students to get the equipment or actually get into a lab. There's been lots of hold-ups this year, and it could be from being away with an isolation from COVID, or the students are sick, or there's been the floods. Sometimes it's just the equipment isn't there in the lab, or they can't get access to the lab and they're running out of time. They still want to do the prac, and they still want to collect data, but it's difficult to get the equipment ready. So I'm going to do the prac and allow students to collect their own data. Okay, so let's have a look at what's going on. The mandatory prac, and I'll talk as if I'm talking to students because they're the ones doing this. The mandatory prac you've already done, we should have done, had you looking at the strength of a magnet at various distances. Now, different schools will have done different things. I usually do the force between permanent magnets, so I have a couple of bar magnets and measure the force as I change the distance. Some people do the magnetic field strength around a current carrying wire as a function of distance. Now they both work and they're fine, so hopefully you've done something like that. The video we're going to do today is it's a modification. Now I'm not going to tell you what sort of modification it is, whether it's a refinement or a redirection or an extension or anything like that. You'll work it out. But I'm going to measure, or look at measuring, the magnetic field inside a solenoid, so a current carrying solenoid. Now I'm going to use a slinky. You see the picture here is a slinky being used as a solenoid. Now I'll show you what a solenoid is like at first. Now I'll just go back to this picture here. Okay, so that's a solenoid that would be typically found in schools. Now the number of turns on that might be 700 turns or something like that, and it's about 14 centimeters, so there's something like 5,000 turns per meter on that. So if that was a meter long, that'd have 5,000 turns. So we talk about turns per meter. Okay, now the difference between a solenoid and an ordinary coil is the ratio, or the comparison of the length to the diameter. Okay, so in this one here, this solenoid, the length is much greater than the diameter. Okay, so that's the key characteristic of a solenoid. Now the formulas really talk about an infinitely long solenoid, but the formulas still work for a shorter solenoid like this. Now, in comparison, a coil that has the length much shorter, so in other words, the length is shorter than the diameter. So you've got a solenoid where the length is greater than the diameter, and you've also got a short coil where the length is much smaller than the diameter. Now that's called a short coil. It'll have its own formulas, and we won't worry about that today. Okay, let's move on. Now I'll just go back to this image. Now in the physics syllabus, or you'll have a formula and data book that goes with the syllabus. In the section on electromagnetism, there's a formula which is B equals mu 0. Now that's mu, the Greek symbol mu, 0. Now that's called the magnetic constant. You can see it in the next line down. Times n, which is the number of turns per meter that I was talking about, times the current. So that's the formula we're going to look at today. Now the magnetic constant, mu 0, has the value in the syllabus formula and data book as 4 pi by 10 to the negative 7 Tesla per amp meter. Now you could multiply that out and it comes to about 1.26 by 10 to the negative 6 as a numerical value. So that's what we're going to look at, how close we can get to the accepted value for the magnetic constant. So just to go over it again, B is the strength of the magnetic field in Tesla. Now you could call that the magnetic field strength, if you like. I think the proper term is just magnetic field, but we often stick the strength in front of it to indicate you're talking about the magnitude and not just the direction. Or you can call it magnetic field strength as a common way of saying it. Mu0 is the magnetic constant I just told you about. N is the number of turns per meter. Now that's equal to N divided by L. So for this one here, I said to you, the number of turns might be 700. The length is 0.14 of a meter. So 700 divided by 0.14 comes to about 5,000. So that's the number of turns per meter. Okay, now a slinky, of course, is much less than that. When you're talking about a slinky, you're only talking about, you maybe will use a slinky that long. It might have 50 turns in 50 centimeters, for instance. So it's not going to be very many. It'll be in the matter of a couple of hundred turns per meter. Okay, let's move on. Now there's the formula again. B equals mu0 n I. Now what we're going to do is keep I constant in this prac. So the current's going to be kept constant, and I'm going to vary the number of turns per meter. Now of course mu0 is a constant as well. So we can say B is proportional to the number of turns per meter when I is constant. Okay, now as N equals N on L, so as little n equals capital N divided by L, if you vary either N, capital N, or L, you can vary the number of turns per meter. So what we're going to do is vary L, the length, from 20 to 70 centimeters. So I'm going to keep this at 50 turns. You can see in the next line it says N is 50 turns. Now it's probably 50 turns. And I'm going to go from 20 centimeters up to 70 centimeters. So stretch it out and measure the field strength in the middle. So I'm going to keep I constant at 2 amps, and I'll measure that with a digital multimeter. I'm measuring amps, the current. Okay, there's the setup I'm going to use. Now I just held that up and you can see it. So the length of that particular chunk of slinky, or solenoid if you like, you can see I've got it 25 centimeters. Now I put a little marker in there so you can read off how long it was. Now I'm not going to tell you how long it is. You'll just have to read the marker. There might be a little bit of parallax error from where I had the lens, but it'll be hopefully it'll be okay. So that's the slinky. Now I'll just go to the next image. I think you can see it better. Oh no, here we go. I'm just labeling some of this stuff. The magnetometer is down there. That's this thing here. You can see it's just a thing that measures magnetic field strength, and it's got a probe or a sensor. Now you can see I've got it poked in the middle of the slinky, so I'm measuring the field strength in the middle of the slinky, the very center of it. Okay, now if you want to work out the direction of current, I've got it so that the current comes up this black wire here. You can see it goes down the back, up the back, and down the front. So you can use your hand rule to work out which way the direction of the pole is, or magnetic field is. I won't do it, but you don't really need to, but if you wanted to do it. And you can see I've got the probe right in the middle. It's a little probe there. It's just, you might be able to see it, it's just a little IC, a Hall effect sensor on the end of a little fiberglass ruler. Okay. Now here's the circuit I'm going to use. Now what I've got is the power supply. Now look, I'll just go back and show you some of these bits and pieces so you're familiar with what's going on. I'll change to this image so it's a bit easier. Now this is just an ordinary laboratory power supply, so nothing, where are we? Nothing tricky in that. Okay, you can go up to 12 volts DC. It does cut out at 5 amps, so if you try and draw a current greater than 5 amps, there's an isolation switch in the back or inside it that will click it off so it doesn't overheat and burn out. I've got the slinky, which is the solenoid part of the image. So I've got the power supply at the top. the slinky at the bottom. The ammeter is just this thing here, okay, and I've got it set on the black is the common, and I've also got it set on the 10 amp scale or the amp scale, not milliamps, so be careful. It's on amps because you're going to go up to 2 amps. And the tricky part of this is this potentiometer. Now that's there so you can change the current. Now it's basically a variable resistor. So here's one example here, okay, and I'll show you some details of it later. But it's just a little variable resistor. It's got a little arm that slides. So when I turn the knob, that was just sliding this along the resistor. So you can pick off any voltage you like from, depending on what you've got this set at. Say you had it set at 6 volts. So it'd be 6 volts all the way along there, 6 volts, and then it'd be 0 volts here. So in this position, that might be 2 volts, okay? So you can vary the slider so you can get 2 amps on the multimeter. Now, the thing is, look, at the bottom I've got here, V equals IR, so I want a current of 2 amps. The resistance for 50 ohms, 50 turns of this slinky is about 1.5 ohms. Right, I've said here, if I measured the resistance of this whole slinky, it's about 3 ohms. So I'll just go back to this image. So I've got about 50 turns, so it's 1.5 ohms. So 2 times 1.5 is about 3 volts. So as long as I have my power supply set at, say, 4 volts. Now I don't want to set it too high because what you'll end up doing is burn this potentiometer out. Okay, if you have a look here, the next formula, if you remember back to Unit 2, P equals VI. So the power output is equal to voltage times current. So I'm talking about 3 volts from the line above times 2 amps, which is 6 watts. Now that's quite warm. If you're getting up to about 10 watts, so if you're having, say, 6 volts across here, you might find this potentiometer gets too hot, and you can feel the potentiometer. It starts to get really warm. Now I've done it many times, and it ends up smoking. It gets so hot. You've got to quickly turn it off so you don't burn it out completely. Okay, so be careful. Don't go too high with your voltage, and it's probably best to stick to a current of between 2 and 4 amps. For the slinky, probably 2 amps is enough. But once you're getting over 4 amps, the power supply is likely to cut out. Look, here's a couple of things. There's that image I just showed you. There's the potentiometer that I just showed you. Now it's also known as a variable resistor or rheostat. It can function in a number of different ways. Now they can handle up to 15 watts. But I'll tell you, at 15 watts, they're pretty hot. They're smoking. And I wouldn't get over 5 watts for those things. They're about $18. Now, a lot of schools will have the big variable resistor or potentiometers or rheostat. You can see the word on there, rheostat. Now they're the IEC ones. Now they're 100 watts, so they can take quite a lot of power. They'll get pretty hot at 100 watts. You wouldn't want to touch them, and they're about 120. Now your school will have those, or it might have the linear ones, but otherwise you can buy these. You buy a few of those. It's good for doing your own pracs if you can't get hold of these. Now the reason I mention about being hot and may burn you, you're going to have to do a risk assessment for your prac. So just keep that in mind. The real main problem with this prac is getting burnt. So just be aware of that. Okay, let's move on. So here's the setup that I used for this prac. There's the circuit diagram again. So there's the power supply. Look, I've got it set on about 6 volts. Now it goes into one side of the potentiometer, and then the current goes all the way around here. So it goes in the ammeter, out of the ammeter, through the slinky. Now I'd have to have that pulled apart. I haven't for the photo, but if those coils are touching, they're going to short circuit. So instead of having 50 turns, it might appear to only be 20. So you've got to keep them just a little bit apart. Now I haven't done that in the photo because it was just for a photo showing you how it's all connected up, but you'll see later I do. So don't let them. What I should have done, I suppose, is dip them in paint so that I can get them close. Then the current goes through the slinky, out the green wire, back to the center peg or center terminal of the rheostat. Okay, so that enables me to change the current inside through the slinky, and that'll appear as a 2 amps on the scale when we see it going. And then of course you have the other terminal going all the way back to the negative supply of your power supply, or negative terminal of your power supply. So that's the setup, pretty simple. Okay, so going back to this, now if I plotted B versus N, okay, B is proportional to N, so I should get a straight line, something like that. Now that's ideally what you should get. Whether you do is another thing. Hopefully you will. And let's have a look at the rearrangement here. So here's the formula again. B equals mu 0 Ni. Now if you divide B by N, you end up with it equal to mu 0 I. Now B on N, this B here divided by N, is just the gradient. So when you get Excel to do a trend line, it'll give you a formula for the gradient, which will include the gradient. So I've got B on N, that is the gradient, is equal to mu 0 I. So if I divide the gradient by the current, which will be 2 amps, I'll get a value for mu. So you just do this prac, measure the gradient, divide by the current, which is 2, and you end up with mu 0. Now hopefully it'll be close, 1.26 by 10 to the negative 6. That's what you'd aim for. And as long as it's within a few percent of that, you can consider it fairly successful. Okay, so here's my first setup. Okay, what I'm going to do, now I'm calling I'm doing 3 replicates of each particular variation in the independent variable. Now, QCAA for physics has recommended what we call a 5x3 approach to doing prac work. That means 5 variations of the independent variable. Okay, in this case, it's the length. So I'm going to do 5 different lengths, starting at 20 centimeters and going up to 70. And for each one, I'm going to do 3, well, you could call them trials. They're tests or replicates. Now, duplicate would be 2, triplicate would be 3. So we can call them in general replicates. I'm doing 3 replicates of each particular length. Okay, so that's a 5x3. Now, let's have a look at what happens here. That's the data. N is 50. Now, it's not 51 or 49, it's 50. Now, it's hard to indicate that 0 there is significant. So what you'd have to do is express it as in scientific notation to indicate that it's 50 or 5.0 by 10 to the 1, not 5.1 or not 4.9 and so on. Sometimes you can put a little bar above 0 to indicate significant. Length is 0.2. You can see here. Now I'm not going to tell you the lengths for all of these. You can work it out. You can read them. So that's 20 centimeters or 0.2 of a meter. So we can calculate N. It's just 50 turns divided by 0.2, and that's 250 turns per meter. And the current you'll see in a little while, not the first few, I'll give you a chance to get a hang of what's happening, is 2 amps. Okay, now I'm going to start it. I'm going to keep stopping it all the way through. So when I press play now, I've had it going with the 2 amps going through it, and you'll see a reading on the screen as something like 0.69, 0.7, something like that. And you'll notice the unit is millitesla. So that's by 10 to the negative 3. Okay, so here we go. Look, I'm just going to stop it and work through this. Now I'll pull this through. You've seen a 0.69, 0.7, 0.68, 0.67, 69, 69, 67, and so on, and 0.7, 0.69. Okay, I'll just run that, let that go through by itself. You can see it. Okay, now what you'll notice is there was a little bit of variation in the reading, so I'll just click on this to see if I can, see if I can get that. Now the best estimate, that is the central tendency if you like, was about 0.68, like I've got on the screen. It tended to be around about that and varied up and down. Now if you heard me say, there was some 0.67s and some 0.70s. So the uncertainty, if you like, could be the B value, the best estimate, plus or minus 0.015. I mean, you take those two away and divide by 2, and you get 0.015, and I'm saying 0.02. If you just do it the way you normally do it, you're going to get no uncertainty, because each of the trials, you basically get the same result for any particular length. So it'd appear that you'd have no uncertainty. So I'm sort of saying to you that in the column when you do uncertainty, don't do your max minus min for the 3 results for that length. Think about it in terms of the variation you're getting for each reading. Now if you say it's 0.02 for all of them, you're pretty safe. Now I don't want you to underestimate the uncertainty, and that's what happens if you don't do it this way. You underestimate it, and I think physics students are notorious for underestimating the uncertainty. So I'm saying to you, make it 0.02 and just say that's what you're doing and see what happens. It should be right. Okay, let's move on. Now what we're doing in the next one is, it's still the first variation of the independent variable. In other words, you're still at 20 centimeters, but I'm doing a replicate. I'm doing the second measurement, and this is trial 2. Now I'm not going to tell you what the numbers are. You can stop this yourself and get the values and stop the video and read them off. So here we go. Okay, so that's that done. Okay, let's move on to the next one. Whoops. This is trial 3. Now I've put an ammeter in the image there so you can see that I'm keeping it 2.0 amps. Now you might say, well, it's 2.02. Now we're only doing any of this to 2 significant figures. The magnetometer is only reading it to 2 significant figures in millitesla. So there's not a lot of point in having this any more than 2 significant figures. There's 2 significant figures in the number of turns, and so I'm just saying make sure it's 2.0, or if you rounded it to the 1 decimal place, it'd be 2 significant figures. So it could be 1.97, for instance, and that'd round to 2.0. So long as this doesn't change too much, we can say that we've kept it constant. Okay, let's see how this one goes and get ready to write these down. Okay, you can see they're all 6.7, 6.8, 6.9. I saw a 0.71 in there, so that's why plus or minus 0.02 is pretty reasonable. Now the next one, whoops, we're going to have a look at a second variation. Okay, so we've done the first variation, that was at 20 centimeters. Now you're going to do a second one, so I'm going to change the length, but I'm keeping the current constant, the number of turns constant, and I'll do 3 replicates. Now I'm not going to tell you the length, but you'll have a look and you can see it by the pointer. There's the pointer there, and you can see it. So this is trial 1. Okay, now whoops, trial 2, here we go. You can see I'm keeping it to 2.0 amps, and trial 3, here we go. Okay, so you should have a total of 6 numbers written down, 6 millitesla values written down, 3 for the first variation and 3 for this variation. So let's move on to the third variation. So this is the third variation. You can see the length I've got it at here. So your chance to copy these to work out the numbers. You can see they're a lot less. They're coming down, of course, as you spread the coil out. And okay, this is trial 2. Now what you'll notice is I'm taking about 5 seconds worth of readings for each one. So this is now replicate number 2 for the third length. Okay, so now we'll move on to the fourth variation, and you can see I've changed the length again. So here we go. Now in these I've started with the power supply turned off, so you can see that I'm getting 0 to start with. Now it's 0.02 there, but it fluctuates as well. So even when I 0 reset, push this button here, it'll often go to 0.01 or 0.02, or might even go to south 0.01. At the moment it's reading to the north. So there it is, 0. Okay, that's that one. Now trial 2. And trial 3. Okay, so let's move to the next variation, which is the fifth variation, and you can see I've got it as set here. You can see the little pointer is on the ruler, and you can see what I've stretched the coil out to. So let's have a look. Okay, turn on. You can hear the clunk as it turns on, and it's staying, look, that's creeping up to 2.1 amps, so a little bit of variation there. But now it's down to 2.04, so it's back to 2.0. Okay, and you can see it finishes up at 2.0 to 2 significant figures. Okay, what happened there? Oh, trial 2 for this length. Okay, and trial 3 for the same length. Okay, now we move to the last one, which is the sixth variation. Now I said to you, we only need a 5x3, so we only need 5 variations of the independent variable and 3 replicates of each one. But I've just stuck in a 6. It was easy to do, and QCAA doesn't say you have to do only 5. You can do as many as you like. You can do 20. When it's expected to be a straight line, 5 is plenty. If there's going to be a curve, if it's some sort of inverse relationship, you'd probably want to do a couple more than 5. But here we go anyway. Okay, trial 1, trial 2. And lastly, trial 3. Okay, so that's all of our data collected. Basically brings us to the end, so you should be able to write all that down, work out your uncertainty, draw the graph, do the line of best fit, put in the error bars, work out whether the value you get for the line of best fit for the gradient, or for the mu0 value, plus or minus the uncertainty, whether that covers the accepted value. It's very close, but I won't tell you whether it does or not. Anyway, we'll see how we go. Okay, there's more of these pracks I've put at seniorphysics.com if you want to look at them. So that's it. Goodbye. Good luck.